Good morning, students. In this video, let us discuss about the current voltage characteristics of MOSFET. So for that, first you take one semiconductor bar. So this is your semiconductor bar which carries current I. So how will you find the current I means? Let us assume that the charge density is equal to QD and velocity of the charge is given by V meters per second. So the current I is equal to QD multiplied by V, charge density multiplied by the velocity of the charge. So now you take one physical structure of N MOSFET. So now you see this figure 2, source drain both are heavily doped N regions fabricated on the P substrate. Okay, so for this particular N MOSFET, what I am doing means I am giving equal voltage to source and drain. That means both are grounded. Okay, what is the concept of this N MOSFET? Till the gate voltage is equal to or greater than threshold voltage, the transistor will get turned on, and any charge that is placed on the gate will be mirrored by channel, yielding uniform channel charge density, which is equivalent to QD equal WCOX multiplied by VGS minus VTH. Okay, now we have find out the channel charge density for equal source voltage and then drain voltage. Next step, what I am going to do means I am going to increase my drain voltage so that I will create potential difference between the source and drain. See, observe this figure 3. Here source is connected to ground, but I am increasing the drain voltage from 0 by means of an external voltage source. So now what will happen? Now the voltage difference between the gate, this is your gate, so the voltage difference between this gate and then channel, this is your channel. Channel is nothing but it consists of charge carriers which are nothing but electrons here. So what will happen means the voltage difference between this particular gate and then this channel varies from Vg to Vg minus Vd. So now I am going to find the charge density at this point x. So how can I find the charge density means the charge density at this point x along the channel, I can write it as QD of x equal WCOX multiplied by VGS minus V of x minus VTH. But what is my ultimate aim? I should find the current. What is the formula to find the current? ID equal to QdV. So now I am going to substitute the value for QD in this particular equation, resulting in ID equal to minus WCOX VGS minus V of S minus VTH of V. Okay, but you should know what is the purpose of this negative sign. Why this negative sign is inserted means charge carriers are negative. Okay, and this particular V denotes the velocity of electrons in the channel. But we know that V equal to mu multiplied by E, where mu denotes the mobility of charge carriers and E denotes the electric field. But E is given as E equal to minus dV by dx. Now I am going to substitute this E equal to minus dV by dx and this mobility mu in this drain current equation, which results in this equation ID equal to WCOX VGS minus V of x minus VTH into mu n dV of x divided by dx. This minus sign and this minus sign results in the positive sign. Okay, we are able to understand the concept. So now I have identified the drain current. Now what is my next step means I am going to put boundary conditions for this drain current. What are the boundary conditions? V of 0 equal to 0 and V of L equal to VDS. This is my boundary conditions. So now I am going to apply my boundary condition from 0 to drain to source voltage, and I am going to multiply both sides of the drain current by dV, and then I am going to perform the integration. See, observe this equation. id dx. Here I am applying my integration from x equal to 0 to L, and the voltage limit 0 to VDS, and here the same equation W COX W mu n multiplied by VGS minus V of x minus VTH multiplied by dV. Now you perform the integration, which results in this equation. Drain current ID equal to mu n COX W by L. Mu n denotes the mobility, COX denotes the oxide capacitance, W denotes the width, and L denotes the length, multiplied by VGS minus VTH into VDS minus half VDS square. Now I have derived my drain current equation for a particular gate source voltage value. Okay, this is my particular gate source value. Okay, now next step what I am going to do means I am going to find this particular drain current for different values of gate to source voltage. Why I am doing this means I should find the maximum value of drain current, okay, which occurs for VGS. So to identify the maximum drain current and the corresponding value of VGS, now what I am going to do means I am going to substitute different values for this VGS, and then I am going to calculate my drain current. Okay, so observe this particular graph. Here I am substituting VGS one value, and then second value, third value. Similarly I am going on substituting my gate to source voltage. Now you analyze this particular drain current. So this is my drain current for this particular gate source value, and this is my drain current for this VGS1, and this is my drain current for this VGS2. Okay, so the drain current reaches the maximum value when I go on increasing this gate to source voltage. Okay, so when the peak value of drain current is obtained means the peak value of drain current is obtained when this particular drain to source voltage is equivalent to VGS minus VTH. You able to understand the concept? What I am doing means first I determined the drain current for one particular gate source value, but I should find the maximum value of drain current. So how can I find the maximum value of drain current means by means of slowly increasing the drain to source voltage. So when I have reached the peak value of drain current means when this VDS is equal to VGS minus VTH, I have derived the peak value. So now what I am going to do means I am going to substitute this VDS equal to VGS minus VTH in the drain equation. Okay, are you able to understand the concept? In this equation drain current, what I am going to do means I am going to find this maximum drain current. Maximum drain current is arrived when VDS equal to VGS minus VTH. So here I am substituting VDS equal to VGS minus VTH, and here also I am substituting VDS equal to VGS minus VTH, and I am solving this entire equation. So which results in this particular equation: maximum drain current ID equal to half mu n COX W by L into VGS minus VTH whole square. So from this what can I conclude means I can conclude that the current capability of this particular MOSFET device increases with gate to source voltage. Okay, and till this drain to source voltage is less than or equal to gate source voltage minus threshold voltage, the device operates in triode region. This particular region of operation you normally call it as triode region. Okay, thank you students.